Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good afternoon to Dr. Zafran and everyone. So, we are from Group 7, and today we will present our proposed IoT monitoring system entitled State Level Crop Productions, Analytics and Monitoring Systems. Basically, the main purpose of this project is to transform historical crop production data into a more interactive and useful monitoring system by integrating Google Colab for data processing and analytics, HTTP Post API for telemetry transmissions, and Thingsboard Cloud for dashboard visualizations and automatic alerts. Throughout these presentations, we will demonstrate the implementation and functionality of our system, explain the identified challenge, justify our design decisions, and evaluate how effectively the proposed system can support earlier identification of crop production underperformance. So, this is my group members. The first one, I would like to introduce Muhammad Amirul Faiz bin Shafi'i. The second one is Muhammad Saidi bin Abdul Rahman. The third one is Muhammad Zul Haziq bin Yasir. And the fourth one is myself, which is Syed Haikal Ahya bin Syed Ikram. For these presentations, each member will cover different parts of the system, including the identification challenge, system methodology and implementations, cloud monitoring functionality, predictive analysis, and overall system evaluations. So, moving to the next slide. Okay, so as Doctor can see here, the main challenge identified in this project is delayed agricultural reporting, which can limit timely response for potential food security risks. Currently, crop production information is commonly presented through static annual reports. Although these reports are useful for historical analysis, the information may not support rapid monitoring and early intervention. For example, crop production can be affected by factors such as pest outbreaks, plant disease, drought, and other environmental disruptions. If a significant production decline is only identified after annual reporting, the response may become reactive rather than proactive. So, this creates a clear chain of problems. First, late information can lead to reactive decision making. Second, an undetected decline can result in regional underperformance. And finally, slow intervention may increase potential food security risk. Therefore, the challenge is not simply the lack of agricultural data. The real challenge is that existing data may not be transformed into a monitoring and early warning system quickly enough to support timely decision making. So this is important because from both societal and health perspective, because stable crop production contributes to food availability and national food security. Going So moving to the next slides, which is rationale for the proposed solutions. To address this challenge, we propose a cloud-based IoT monitoring and analytics systems. The rationale behind our solution can be explained through four stages. First is the problem. Static annual data can contribute to reactive decision making because abnormal production patterns may not be highlighted automatically. Second is the need. We require better visibility of crop production trends together with analytical and predictive capabilities that can identify possible underperformance. Third is our proposed solutions. We use Google Colab to process and analyze the crop dataset, generate analytical and predictive outputs, and transmit the process telemetry to Thingsboard Cloud. Finally, the expected outcome is an early warning and decision support system. Instead of only viewing history records, user can monitor production trends through a cloud dashboard and receive alerts when abnormal conditions are detected. We selected this approach because it is relatively low cost and scalable rather than immediately deploying physical sensors across all agricultural areas in Malaysia. The, the system first utilizes existing only historical data and transform into SQL Cloud telemetry. These allow the project to demonstrate three important capabilities, which is data analytics, cloud-based monitoring, and automated alerts. Therefore, our proposed solution aims to shift agricultural monitoring from a delayed and reactive approach towards a more proactive and data-driven decision support system.
Let's look at the data running through our system. We are using 864 historical records from OpenDOSM, covering 16 states, 6 years, and 9 crop types. Our data flow through 3 stages. First, the original datasheet gives us raw numbers like planted areas and production. Second, we use the calculate derived analytics, which are our calculated yield, prediction, and production gaps. Finally, this goes into our cloud monitored series to track trends and context on the dashboard. This slide shows how our system works from end to end. The process is simple, from online data to the Python analytics, then JSON telemetry, furthermore cloud dashboard, and the last one is alert. We use two main tools to do this. First is Google Colab. On the left is our brain. It handles all the data cleaning, analysis, and AI predictive modeling. Thingsboard on the right is our cloud platform. It receives the data, runs the visual dashboard, and triggers food security alarm if production drops. Here is how we actually set it up, split into three simple steps. Step 1. Load and inspect. We bring the raw CSV crop data into Google Colab to check it. Step 2. Build endpoint. We create a virtual device in Thingsboard and get a secure access token so Colab can talk to the cloud. Step 3. Send and verify. Our Python script send the data raw by row as JSON payloads. The server send back an HTTP 200 OK message to confirm it received the data successfully, updating our dashboard. Lastly, why did we choose HTTP post instead of other options like MQTT or CoAP? MQTT is great for live second and by second sensor streams, but it needs an extra broker setup. CoAP is good for low power hardware, which we don't need here. HTTP post was our best choice because it works instantly with Python, support JSON perfectly, and most efficient tool for the job, and easily confirm success.
Okay, now we move on to next page and look at our Thingsboard dashboard. This is where all the data processings come to life and become something users can easily monitor. As you can see on the slide, we focus on three main visualization capabilities. First, we have the time series charts. These line graphs are crucial because they let us track the planted area and production trends over time. Instead of just staring at numbers in a spreadsheet, we can easily spot the changes. Second, we use indicator cards at the top. This card gives us instant context like the specific state, for example, wilayah Persekutuan Labuan, and the crop type like vegetables. It basically reduces the effort needed to interpret the data. And finally, we have the alarms table at the bottom. This is where abnormal events become visible immediately, prioritizing the user's attention exactly where it's needed. Our system goes beyond just displaying numbers. What we do here is take the actual production and compare it against a predicted or expected target. When the system detects a significant deviation, meaning the actual production drops below the target, it automatically triggers a Thingsboard alarm. You can see the evidence of this on the slide. The system successfully logs a minor severity alarm when tested. Why is this meaningful? Because it makes crop underperformance visible right away, rather than keeping it hidden in an annual report for months. This automated alarm allows the authorities to investigate and intervene much earlier. Okay, now let's look at the flow of our predictive analytics. This part was specifically designed to hit the excellent criteria in our project. Instead of just doing descriptive monitoring, which only tell us what happened in the past, we integrated a predictive flow. We start with the historical inputs like the area, year, state and crop. Then the system makes a prediction for the expected crop production. Next, it runs a comparison between the actual data and the predicted data. Finally, there's a negative deviation. It takes action by triggering the alert. So, by transmitting these three significance data series to the cloud and running an efficient JSON script to handle the comparisons, our system acts as a proactive early warning tool, not just data display. Okay, let's evaluate the effectiveness of our system. Did we actually solve the challenge we brought up at the start? Let's compare the before and after. Before this IoT workflow, the authorities relied on static reporting. They had to wait for annual PDF or Excel records, which caused delayed awareness and forced them into a slow reactive response. There was zero integrated early warning. After implementing our proposed IoT system, we now have a cloud accessible monitoring. We have clear trend visibility across different states and crops, predictive comparisons, and most importantly, an automated alarm for underperformance. So, to conclude this section, yes, our system is highly effective as a low-cost early warning and decision support prototype. It gives authorities the time they need to secure the food supply before a crisis hits.
Evidence-based justification of design decisions. For our existing online data, we search it on OpenDOSM for historical state-level crop records. This is to avoid immediate nationwide hardware deployment by using software. And then cloud platform. We use Thingsboard. It can do telemetry reception, time series widgets, and alarm management to visualize our data. And then communication, we use HTTPS because it fits Python notebook, structured JSON, and response verification. And then finally, predictive alert to know the actual versus expected production. Because we can support the earlier identification of underperforming regions. Now for the limitations and future improvements. What are the current limitations? The first one is historical annual data are not live field measurements since the data is in the past and not in real time. And the next one is state level isolation cannot pinpoint individual farms because the state level is a large production, so we cannot know which farm is performing and which farm is underperforming. And then the productive reliability depends on broader features and validation since we are limited to only Thingsboard and Google Colab. Thingsboard demo, we cannot have accurate prediction and uh, reliable prediction. Then next one is what can we do to improve it? Integrate live weather APIs, rainfall, temperature, and humidity since these three factors heavily affect the crop production. And then pilot low cost soil moisture or temperature sensors because we can directly monitor the soil moisture and temperature sensor to know what is the problem for our crop production if they suddenly drop. Then finally to expand to this farm level and stronger ML validation to pinpoint exactly which farm is performing and underperforming. So to conclude, the system transforms static crop records into cloud telemetry, dashboards monitoring, predictive comparison, and automated early warning. This is to record the crop productions by state and to track any performance of the regions to know whether they are performing well or not, so we can solve any of the problems. And then I will also show the live demonstration sequence for our Google Colab and Thingsboard. Okay, so now for the live demonstration sequence, let's go to our Google Colab. So the first cell, we put this command. This is to let the Google Colab know how to interpret data, such as do any calculation and plot graph. And then next one is how to mount our Google Drive to our Google Colab. So Google Colab can have access to our Google Drive. And then next one is set the data path So we can specify which data can the Google Colab access. So I put the folder name here, IT assignment, and the file name crop.state.csv is here. So the data we already obtained from my dosm. Then next one is we go to the Thingsboard, to the device part, the crops production by state, and then copy the access token and paste here. And then we also open the check connectivity, and then follow copy the HTTPS link, beginning with HTTPS until telemetry, which is here. Then next one is this command is to put all the rows in our data and send it to the uh, our Thingsboard. Then yeah, then all this 200 means each row is successfully sent. So and then we go to the Thingsboard, and then since we already run it, if I refresh it, it will turn active. Here it's already active. Then we can go straight to the our dashboard, cross production. Okay, so for our dashboard, we let AI configure it to get the best widgets possible, and then also create a trend chart, which is project area and production trends against time. Okay, then this graph is the blue line is planted area against time, and green one is production amount against time. And then we also added the production alarms to alert us in case of drop in production amount. So since we can see from the graph, the production is really low compared to previous hours. The severity is major. If it does not drop much, the severity is minor. Okay, and then next we go back to our Google Colab, and then this is for the command for our alarm I shown earlier. Then next one is the plot. Here we run it. So this graph, this scatter graph shows the production amount against date, which is here is the production amount times 10 to the power of 8, and then here is date. Okay, and then the next one is also the graph. So this is all the command for the colors, the states from the data. Then if you run the last one, we can get the production trends by state. So each color represent different state, where the top one is Malaysia, since it is the accumulation of all states, so it has the highest amount. And the y-axis is also production times 10 to the power of 8, and the x-axis is the date of the production. So by doing this, we can check the trend and the production amount. So we can check at which time the production is the highest and which time is the lowest. So we can predict any trend in the future, as well as to solve any production problems. So that is all from us. Thank you.